Welcome back to the TrueGrid tutorial series. TrueGrid is a hex mesh generator that uses the projection method. The meshes that TrueGrid creates are of unparalleled quality and speed. The mathematician Dr. Robert Rainsberger, founder of XYZ Scientific Applications, perfected the projection method when he wrote TrueGrid. If you haven't already watched the building blocks and the screen navigation lessons, please do so before you watch this lesson. This lesson is an introduction to the projection method. In this lesson, we are going to create a disc-shaped mesh from a multi-block mesh that we call the butterfly topology. We will project that mesh onto a cylinder surface to form our disk and explore several ways to use cylinders and planes to project. We will introduce and illustrate the use of the index bars in the computational window. We will illustrate the value of collapsed blocks for a more efficient mesh building, and we will create block boundaries to remove collateral nodes. Lastly, we're going to introduce the uniform smoothing algorithm. We strongly suggest that you follow along with an active session of TrueGrid running in another window. From time to time, you may want to pause this lesson and replicate what we've just done in your live session of TrueGrid. If you don't have TrueGrid, please visit our website and request a 30-day free trial version of the software. We are going to start TrueGrid in the control phase without a command file. We do this by launching the TrueGrid program and then selecting Cancel instead of selecting a file. This opens TrueGrid in the control phase and it displays the text window. Select Parts option and then the Block option. The Block dialog box will appear. Let's build a rectangular three-dimensional mesh made up of 9 blocks, 3 by 3 by 1, with each block containing 6 elements in each direction. We commonly refer to this mesh as a multi-block mesh. To do this, we're going to enter the indices and coordinates shown on your screen. Note the difference between the indices is 6. The same as the number of elements in each direction in each block. After you've entered these numbers, hit execute and quit. This is a great time to pause your lesson and build this same block mesh in your live session of TrueGrid. Let's look at what we've built. We have a 9-block wire mesh and each block contains 6 elements in each direction. Our next step is to delete the 4 corner blocks that we will not need to form the butterfly topology. Change the picture to the wire mode so that you can see all of the wire mesh structure. To select a block, start in one corner and to press your left mouse button and drag the cursor to the furthest opposite corner and release. When the block turns cyan, this signifies that you have successfully selected the block. Notice in the physical window the corresponding block has also turned cyan. Now simply delete the block. Notice that the newly exposed faces appear magenta in both windows. Click anywhere in either window and the magenta returns to green. Notice that different colors are used to indicate the selection of different mesh elements. Red is used for nodes, blue is used for edges, yellow is used for faces, and cyan is used for blocks. Now, delete the other 3 corner blocks. What if I had been hasty and accidentally deleted the wrong blocks? I could simply select Undo to back up for each step that I wish to undo. I'll quickly get us back to our desired butterfly topology. Now we're going to add a cylinder surface to project our faces onto. We want to pick the center point of the mesh to also be the center point of the cylinder. In this case, the center is 10, 10, 3. To find the center point of a mesh, take the midpoint of each coordinate range of x, y, and z from the block command. For our cylinder, z can be any value because the axis is the z direction. Select the Surface option and SD, short for Surface dialog. This shows the surface types that you can pick from. Select the cylinder. We are going to name our cylinder surface 1. The point on the axis of rotation is x10, y10, z10. The vertical parallel on the axis of rotation is x0, y0, z10, with a radius of 10. We could have picked a different radius, but the radius of 10 will place the cylinder just beyond the faces that we're going to project. Execute quit and draw. Let's select the faces at the end of the butterfly topology and project them onto our cylinder surface. First, I'll show you the simple method of selecting the faces one at a time using your mouse, and then I'll show you another technique that is faster but takes some practice to become proficient. Using the mouse, I have selected one end face. Select Pick, then Surface, 1, Enter, and project. TrueGrid took the end face and projected the nodes to the closest point on the cylinder. Select Display List and Show None to hide the cylinder surface so we can examine the newly projected face. Using the projection method, TrueGrid evenly spread the nodes across the surface, resulting in a high-quality mesh by distributing the distortion across all of the affected elements. This is not only the case for the surface elements, but also the case for the internal elements of our mesh. I'm going to speed up repeating the projection of the remaining 3 faces. Examine what we've built. It is symmetrical and the elements are evenly distributed to result in a high-quality mesh. Now I will show you a faster technique. Use the undo option 4 times to undo the projected faces. Notice the 3 index bars along the side of the computational window. They are made up of a combination of dots and bars. Notice that the index bars have a dot aligned for each plane of nodes and a bar representing each plane containing faces. Notice when you select a mesh component such as a node, edge, face, or block, the index bar segments turn red in correlation with the components you have selected. You can only select faces on a single plane at a time from the mesh image using the mouse. With the index bars, we can select multiple faces on different planes at once. I have selected the nodes and bars on the index bars to select all 4 end faces at once. This time, we're going to use our mouse to select the cylinder surface from the image in the physical window. Hover over the cylinder and left-click. Notice the surface turns cyan and white to indicate that it has been selected. Select Project, and all 4 faces project simultaneously. We are going to add a second surface, a plane that will intersect our butterfly at its center point and at the opposite interior nodes, dividing the mesh in half diagonally. We are going to select SD to open our surface dialog window, and this time we're going to pick the option Plane by Point and Normal. This will be surface 2. Our point on the plane will be x10, y10, z10. Our normal vector, x1, y1, z0. Execute quit. Now add a third surface, another plane that will intersect the first plane at the same center point and be perpendicular to the first plane. Select SD and again pick Plane by Point and Normal. This will be surface 3. The point on the plane is x10, y10, z10. The normal vector is x-1, y1, z0. Execute quit. Let's select Labels, then Surface, and Draw so that we can see the surface names in the physical window. Zoom in and make sure that our 2 new surfaces are in the correct location. They intersect in the center of the mesh, and they are perpendicular to one another and bisect the butterfly's center block on the bias. We are ready to project the side faces of our 4 wing blocks to form our disk. There are a total of 8 faces to project. We can project them one at a time or 2 at a time. Again, I will show you the simple method by using the mouse to manually select 1 or 2 faces at a time, and then I'll show you a technique to make this entire disk projection very efficient. I'm going to select one side face and then project it onto the adjacent plane. Manually select the face and then select the surface from the physical window. Let's do one more that way. Now let's select 2 adjacent faces at the same time using the index bars. Select the node and bar combinations to select the 2 adjacent faces. Select the desired surface and project both faces. I'll repeat this for the last 4 faces, projecting them 2 at a time. Hide all of the surfaces and rotate the image. We have learned the basic steps to project a multi-block mesh onto 3 surfaces to form a disk. Now, I'll show you a technique to project a disk with only one projection and only one surface. I'm going to end this session of TrueGrid and start a new session in the control phase. Select parts, then the block, and the block dialog box will appear. We are going to build our same 9-block mesh as before, but this time we're going to collapse or flatten all but the center block. The IJK indices are the same as in our first block mesh, but this time we're moving the XYZ coordinates as displayed. Notice that the 8 exterior blocks are collapsed against the side faces of the center block in the physical window. In the computational window, however, all of the 9 blocks are still visible. Let's select and delete our 4 corner blocks. Now we've returned to the familiar butterfly topology in the computational window. The wing blocks are still in both windows, but they are collapsed in the physical window. Let's add a cylinder surface. Select Surface, then SD, and select Cylinder. We are going to name our cylinder Surface 1. Now we're going to enter the coordinates for the point on the axis of rotation. For our cylinder, it's x0, y0, z0. The vertical parallel to the axis of rotation is x0, y0, z1 with a radius of 3. Execute quit. Let's select all 4 wing end faces using the index bars. Select the cylinder from the physical window and project. Notice that because the wing blocks were collapsed, we were able to project the faces simultaneously. This is because the wing block side faces had no thickness, and thus the starting point for the nodes on the end of the faces share the same location as the sides of the center block. This results in a fine quality mesh as is. However, with a few additional steps, we can improve the quality further. We are going to run this mesh through a smoothing algorithm that will shift the nodes to smooth and even out the element distortion throughout the entire mesh. To do this, we first glue the adjacent wing block side faces to one another so that they share the same nodes before smoothing. If we don't glue these block boundaries, the smoothing algorithm will consider all of the wing block side nodes as fixed, but we want them to participate in the smoothing. By gluing the side faces, we remove all of the collateral nodes and incorporate all of the disk nodes into the smoothing process. I have selected one of the 2 faces I want to glue together. Notice that you can see the face that I have selected here in yellow in the physical window. Now I go to the Interface menu and select BB to define the block boundary interface. The block boundary dialog box appears. Move your cursor into the BB dialog window and hit F1, and this will fill in the boundary constraints based upon the face that you have selected in the computational window. This will be the master face for the block boundary interface number 1. Execute quit. Now I'm going to select and identify the second face that I want to glue to the first face in block boundary interface number 1. Select the second face in the computational window. Select Interface, select BB. Move your cursor into the dialog window and hit F1. This will be the slave face for the block boundary interface 1. Execute quit. Repeat the same process to set the other 3 block boundary interfaces. I suggest you always reset your mesh first and then start in the upper left-hand corner working clockwise. Now we are going to smooth the mesh. Select Mesh from the main menu and then Uniform. The Uniform dialog window appears. We are going to smooth the top faces of our mesh, and then we are going to smooth the bottom faces of our mesh. In the computational window, select the 3 center vertical block faces, and then select F1 to populate the region constraints in the Uniform dialog box. Select Another Region option from the dialog box, and then select the top left face and hit F1. Repeat for the right top face. You have all of the faces selected for uniform smoothing. The smoothing algorithm is made up of a set of differential equations that systematically adjust the nodes to smooth the mesh. As the iterations of the smoothing algorithm runs, the nodes are repositioned to be as close to orthogonal as possible with the adjacent elements, one after the other, until the node movement becomes 0 or close to 0. Naturally, as each node is repositioned, there is perturbation impacting the neighboring nodes. Think of this as a wave of perturbation moving across the surface until the node repositioning is insignificant. Once the algorithm results in a 0 change in the node location, the iterations will stop. We are going to set the dialog box to run a maximum of 72 iterations to ensure that we have sufficient smoothing. The iterations will run across the surface much like a refractory wave, flowing back and forth 4 times. This should be sufficient for this mesh as it only has 18 elements spanning in its x-axes, and this will yield 4 repositionings per node. We're going to set the minimum change to 0 and the interpolation parameter to 1 for this example. We will go more in depth about what these mean in another lesson. Select Execute Quit, followed by Draw to see the smoothing of the top surface of the mesh. Now let's flip the mesh over using the Rotate option and repeat by smoothing the other side of the mesh. I hope that you've learned a lot in this introduction to the projection method lesson. This is one of our basic lessons. We suggest that you complete all of the basic lessons before moving forward to the intermediate lessons. We suggest that you next watch the basic lesson named Projecting a Sphere. Thank you.